Hello everyone, welcome back to my YouTube channel. Myself Tanusiriam, currently pursuing BE in Sri Venkateshwara College of Engineering, Bengaluru, in the Department of Electronics and Communication Engineering. And today the topic subject is about the applied chemistry for EEE stream, and the topic is Gauss divergence theorem, and the subject code is BPHY202. And the table of the contents we are going to discuss in this video is introduction to Gauss divergence theorem, statement of Gauss divergence theorem, understanding the divergence of a vector field, illustration of flux through a closed surface, application of electromagnetism, visualization of divergence and flux, practical applications in fluid dynamics, Gauss divergence theorem 3 dimensions, and computational tools for Gauss divergence theorem. Introductions to Gauss divergence theorem. The Gauss divergence theorem, also known as Gauss theorem or the divergence theorem, relates a surface integral over a region to a volume integral taken within the region. It establishes a relationship between the flux of a vector field through a closed surface and the divergence of the vector field within a region enclosed by that surface. The theorem is named after a German mathematician and physicist Carl Friedrich Gauss. Statement of Gauss divergence theorem. The Gauss divergence theorem states that the outward flux of a vector field through a closed surface is equal to the volume integral of the divergence of the vector field over the region enclosed by the surface, and mathematically it can be expressed as triple integration of delta dot f into dv is equals to double integration of f into dA, where delta into f represents the divergence of the vector in field f. This theorem is a fundamental result in vector calculus with applications in physics, engineering, and other fields. Understanding the divergence of a vector field. The divergence of a vector field at a point is a measure of how much of the vector field is spreading out or converging at that point. Mathematically, the divergence of a vector field f is equals to lesser than p comma q comma r is given by delta dot f of dou p by dou x and dou q by dou y plus dou r by dou z, where dou by dou x, dou by dou y, and dou by dou z are the partial derivatives. Positive divergence indicates a source while negative divergence indicates a sink in the vector field. And the physical meaning in the divergence of a vector field, we may regard the divergence in the vector field at a given point as a measure of how much the field diverges or emanates at that point. Illustration of flux through a closed surface. In the context of Gauss divergence theorem, the flux of a vector field through a closed surface is the amount of flow of the vector field across the surface. Positive flux indicates an outward flow, while negative flux indicates an inward flow through the surface. The Gauss divergence theorem relates this flux to the divergence of the vector field within the enclosed region. The Gauss law is given by pi is equals to integration of E vector dot ds vector is equals to q by epsilon naught. Application of electromagnetism. The Gauss divergence theorem is extensively used in electromagnetism, particularly in the study of electric and magnetic fields. In electrostatics, the divergence of the electric field is related to the charge density, allowing for the calculation of electric flux through the closed surfaces. Similarly, the magnetostatics, the divergence of the magnetic field is related to the absence of magnetic monopoles. Visualization of the divergence and flux. Visualizing the divergence of a vector field and the flux through a closed surface can provide a deeper understanding of the Gauss divergence theorem. In the image shown, the vector field is diverging outward from the center, resulting in the positive divergence. The flux through the closed surface is proportional to the amount of divergence within the enclosed region. And the practical applications in fluid dynamics. The Gauss divergence theorem finds application in fluid dynamics for analyzing the flow of fluids to the surfaces. By relating the divergence of the velocity field of a fluid to the flux of the fluid to a closed surface, engineers can study fluid flow patterns and properties. This application is crucial in various fields such as aerospace engineering, civil engineering, and environmental science. Gauss divergence theorem in 3 dimensions. The Gauss divergence theorem holds in 3 dimensional and can be applied to a vector field in any dimension. It provides a fundamental connection between the behavior of a vector field within a region and its flux through the enclosing surface. Understanding and applying this theorem can simplify complex calculations involving vector fields and their properties. Computational tools for Gauss divergence theorem. Numerical methods and computational tools such as software programs like MATLAB and Python are commonly used to calculate divergence and fluxes in practical scenarios. These tools enables engineers, physicists, and mathematicians to analyze complex vector fields and sufficient surfaces efficiently. Visualization software can also aid in illustrating the concepts of Gauss divergence theorem for educational purposes. And the conclusion of the Gauss divergence. The Gauss divergence theorem is a powerful tool in vector calculus that relates the divergence of a vector field to the flux through a closed surface. Understanding the theorem is essential for various applications in physics, engineering, and other disciplines. By visualizing and applying the Gauss divergence theorem, researchers and practice can gain insights into the behavior of the vector fields and their interactions with surfaces. So thank you for watching my video. Please like, share and subscribe to the channel. Thank you.